Hi guys, and welcome to this video on radians, and hopefully by the end of it you'll feel like this picture. Love them. Now, before we go any further, let's make sure our calculator is set to work in radians. So you can go Shift, Setup, change the angle unit to radians. And a little R should appear on your screen, and previously you would have had a little D for degrees. Now, some things you need to memorize. So formulas you need to know. So area of a sector and arc lengths, perimeters, that's what this lesson is all about. And in degrees, you used to be using these two formulas here. But if you just look across, they're much smaller, especially this one, far easier to use. So you need to know the area of a sector is half r squared theta, and the arc length is r theta. Theta here being in radians, and theta here being in degrees. This is one of the reasons radians is so useful. So for this question here, we have a semicircle, but this bit is cut out here. So we have a triangle cut out, and we're kind of ignoring this segment here. So this could be like a badge design, or I don't know, something to do with design and fashion maybe. So what do we know? We know this is a diameter. So what I like to do, as soon as I see that, we know this is the center, is I'm going to mark on these three lines being the same length. And we're told this angle here in this text, but we can see that for ourselves. It's part of this sector here. Now, it's important to understand how big this one is, which is pi minus 3. So normally you would have said 180 degrees on a line. You need to know that 180 degrees is equivalent of pi radians. So that's why these two must add up to pi, 2/3, 1/3, very simple. So let's actually start off by looking at the area of this shape. Okay, so the area. So we've got two sections, section 1, section 2. Section 1 is a triangle. Now, if you think of the formula half AB sine C, A and B for this angle here are both radii, so we can change it to this. So half AB sine, and I'm just going to put pi over 3 in here. Now we have the radius, so I probably should have put this in all at the same time. So that's going to be 4, right? 2 squared is 4, sine pi over 3, which is 2 sine pi over 3. Now there are some things that you should memorize, and this ratio is one of them. So sine pi over 3 is equal to root 3 over 2. So it's 2 lots of root 3 over 2, and these will cancel, so you end up with a nice exact answer of root 3. Okay, let's have a look at section 2. Well, this is area of half r squared theta, because it's the area of a sector in radians. So it's just half. R squared again is 4, and theta is 2 pi over 3. So half of 4 is 2, so 2 lots of that is 4 pi over 3. So the total area is root 3 plus 4 pi over 3. That's a nice exact answer, so I'm going to leave it there, but you could hit your SD button and round it if they ask you to, which is no problem at all. Let's have a look at perimeter. Let's have a look at this. So perimeter. Well, the perimeter is going to be this length AC plus the arc BC plus 4, which is the diameter across here. Well, this is going to take me quite a long time, so this video is not really about how to find AC, so I'm just going to tell you very quickly. But we've got 3 sides involved, 2 given, 1 unknown, and we've got the angle opposite. This is the cosine rule, so you can use the cosine rule to find that, easy peasy. Arc length of BC, well, that's just r theta, which is just 2 lots of 2 pi over 3, which is 4 pi over 3 plus 4. So once you use the cosine rule, pop your answer in there, add this together, and you've got the perimeter. So it's pretty easy, but I'm not going to waste video time explaining the cosine rule. Okay, here's another one. So we've got the points A and B lie on the circumference of a circle. So let's draw ourselves a circle. That's probably one of the worst circles ever drawn, but that will do. So A and B, they're on circumference. So I'm going to put A there and B there. Yeah, let's see. This might go horribly wrong and I'll redraw it. But we know this is 8.5, and that's A and that's B. So the point C lays on the major arc of AB, right? So this is pretty useful. So here's the minor arc, the smaller one, and here's the major arc. Okay. So I'm going to put point C just smack bang in the middle. Why not? We're told angle ACB, so I'm going to draw some lines in here. A to C to B is 0.4 radians, so a little C there. And calculate the length of this minor arc. Okay, this is a pretty simple question if you see the circle theorem. So that's going to be 0.8 radians. Angle at the center is always twice the angle at the circumference. So the arc AB is equal to r theta. So r is 8.5, theta is 0.8. So let's just type that into my calculator. So 8.5 times 0.8 is 34 over 5. So that's 6.8, yeah. Or 6.8 centimeters. Nice and simple, that one. Okay, this question, less simple. Now, we have a sector here, OAB, it's a big sector, and then we have a circumscribed circle in the middle with center C. We can see that O and B and O and A are tangents, but they're telling us that as well in this text up here. So the fact that that's a tangent, and they've drawn the radii going to the tangent, immediately I want to put a right angle sign here, so I'm going to. Now when I have lines that are the same length, I always like to mark them on. I think that's really useful. Okay, so we have to show that r sine theta equals little r 1 plus sine theta. Now, how do you start to do this question? Well, because I see this, I see a ratio, and I know sine theta, and you know too, is equal to the opposite of a right angle sided triangle divided by the hypotenuse, and I have a right angle triangle. So my first port of call will be to investigate that right angle triangle using that ratio. So let's just draw that out so it might be easier to see. So that's O, that's C, and that's E. Right, so at the moment, all I know is that is R. I don't know anything else. Okay, because we're using the sine ratio, if I put theta to be here, I would need both of these. And I've got this one already. But this would be the adjacent to that angle. So if I put theta to be here, then that would be the opposite, and that would be the hypotenuse. That means I only have to find out this one length here. So it makes sense to me to put theta there. And up here, we're also told something about this angle. We're told this angle here is 2 theta. So this must be just 1 theta, so it just works out that I've done that. But can I just half that? The answer to that is yes, because if you think about from a point, tangents from a point, they are equal in length. So OD equals OE. They both have the same radii, or radius, and they both share OC. So using the congruency rule of side, 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 these must be identical triangles, and therefore it's pretty safe, well, it's certainly safe for me to just to half this value. Okay, so if this was 70, this would be 35. If this was 80, this would be 40. So that's 2 theta, that's 1 theta. Okay, so let's start using this. So we've got sine of theta is r over the hypotenuse. So we have to find a length for this. I'm actually given that, aren't we? So this is capital R. So this means O to T is capital R. C to T is a little r. So this one must be, I'm just going to rub that out and do it properly. This one must be capital R, O to t, take away c to t, and that's going to leave us with O to c. So hopefully we can rearrange this to get to that. So let's multiply by this denominator. There's no fractions involved, so it makes sense to get rid of that. So we've got sine theta, lots of r minus r. I put this in the bracket because there's two terms. So looking here, I've got r sine theta. So let's expand this bracket. So I've got r sine theta minus little r sine theta, and that's equal to r. And we have to make this the subject, so let's do that. So r plus r sine theta, and there we have it. Factorise for r, and we're there. So like I said at the start, I'm not sure how to begin this question, but looking at this, I have a sine ratio, I have a right angle triangle. It made sense for me to explore that triangle, and we have it. Okay, here's another show that question. This one is far more difficult, so if you can understand this, you're not going to have any problems at all with this radians topic. So we have a diameter, so that's a radius, and that's the same length as well. We know the area of this triangle COB is equal to the area of the shaded segment, and we just have to show that. Okay, so let's write a few things down. So let's write area of triangle COB. Well, we know that is equal to half r squared sine theta. Now, we can't actually do anything because we've got no values at all. Oh, we can, because no, theta is theta. So, right, that's it. It's finished. That wasn't too exciting. So let's focus now on the shaded segment here. So, area of the segment, that is equal to the area of the sector minus the area of the triangle. So I'm going to put triangle AOC there. Alright, so the sector. The sector needs an angle, so does the triangle. So that must be pi minus theta, because angles on a straight line add up to pi radians, or add up to 180 degrees. So area of the sector is half r squared theta. Area of a triangle is half r squared sine theta. Don't be tempted to collect these. That's not a like term. There's a sine ratio, and there's not one here. So half r squared theta, and theta, sorry, is pi minus theta. So that's where it gets confusing, because we're using a symbol in our formulas which is featuring in this question. If that was an x, it might be a bit easier, and that would be pi minus x, and you wouldn't make the confusion, maybe. And this one is half r squared sine pi minus theta. Ah, I see. This is where this question is tricky. Now, let's go back to your sine graphs. I've mentioned this in the last video. So if this is in radians, that is pi. If we take 0.5, if we do the inverse sine of 0.5, we're going to get a value here. And it would be exactly the same as that value there. And you're used to writing in degrees, sine theta is sine 180 minus theta. So sine theta is also equal to sine, so that's in degrees, sine pi minus theta, that's in radians. So instead of writing this last bit here, we could just write half r squared sine theta, because it's exactly the same. Now, can't do anything with this one. Don't be tempted to write a theta here, because that isn't a sine ratio. There's no symmetry involved in this at all. But we also know this is equal to half r squared sine theta. Yeah, that's the triangle COB. Right, so let's just play around with this now, and hopefully we get to the answer. So these are like terms, this part and this part. So let's add those, and we're going to get a single r squared sine theta equals half r squared pi minus theta. Yeah, so if you didn't make this connection here, this question is going to be really difficult for you. Right, there's no r's. We're not trying to make any r's there, so let's get rid of the r's. They're the same on both sides, so we can just divide them or just ignore them. Oops. Dividing them is proper, I guess. So half pi minus theta. There's no halves involved, so let's make sense to get rid of that. So let's times everything by 2. So we get 2 sine theta equals pi minus theta. And what are we making the subject? We're making pi the subject. So let's add theta to both sides. We have 2 sine theta plus theta. And is that what we were trying to work out? Yeah, I've just popped it around the other way. Perfect. Right, that's a decent question. If you've understood that, then there's no stopping you now. So best of luck, guys, with that. And, yeah, please reach out if you're struggling.